Hello, everyone, and welcome to a review of selected Organic Chemistry 1 topics. Okay, so as I mentioned, I'm putting together this short review of Organic Chemistry 1 topics. It is not meant to be inclusive of every single OChem 1 topic, but the most important topics are included. Some topics are not included because I plan on reviewing those throughout the semester as we learn some new principles of organic chemistry. The first thing I wanted to start with is functional groups. I just wanted to remind you guys that you should know your functional groups. So if you might have forgotten some of these, it would be good to make flashcards to review them. So the Klein Organic Chemistry textbook reviews reactions and properties of functional groups, and usually one or more functional group is highlighted in each chapter. So we will be reviewing functional groups as we go, but it's always good to know them. For example, you should know that when you have a carbon, like a methylene here, attached to an OH group, this is called an alcohol. However, when that OH group is bonded to a carbonyl on the alpha carbon, or the carbon directly attached to the OH group, that would be called a carboxylic acid. You can review these if you have the Klein textbook in chapter 2. Let's talk about resonance. Resonance is an extremely important topic that was covered in Organic Chemistry 1 and will be important throughout the entire year, including the second semester of organic chemistry. So recall that what we call resonance is delocalized electrons in a series of overlapping p orbitals. So for example, you can see we have an allylic carbocation here. So there are p orbitals from the overlapping pi bond on these two carbons. And there's also a p orbital on this carbon that in this particular structure shows that it's empty. But this one structure is not good enough to understand the true structure of the allylic carbocation. We actually need to draw two structures using this double-sided resonance arrow to denote that the true structure is actually a hybrid of these two structures. And because they're equally significant, it's a 50-50 hybrid. And what that tells us is that the electron deficiency in the system, meaning the positive charge, is actually delocalized or spread out, not over the entire 3-carbon system, but it's shared between the two terminal carbons. And that's what these resonance structures show, that they both actually have part of the positive charge. You can see the overlapping p orbitals here. So if there are 2 electrons in a pi bond, and there's a p orbital on the very next carbon, with all 3 p orbitals should be able to overlap, which means that the 2 electrons in the pi bond are actually delocalized or spread out over all 3 carbon atoms. So we use these resonance structures to show us the more accurate picture of where the pi electrons are in the structure. So recall that when you have greater electron freedom, that makes it so that the electrons are more stable. So overall, the delocalization of electrons in the overlapping p orbitals or pi system stabilizes the molecule. Also, the charge is spread out. Instead of having a full positive charge on one single carbon atom, instead we share the positive charge over 2 carbon atoms, which is a lot more stable than having a localized full positive charge on 1 carbon atom. So overall, resonance is stabilizing, and that's an important point to know. So hopefully you recall when you took Organic Chemistry 1 that you started using curved arrows to show electron movement. Curved arrows are super important, and it's important to me that you master the skill of drawing curved arrows properly. We talk about the arrow tail, that's where the arrow starts, usually where people start drawing their arrow. And then it moves over to the arrow head. right? And both of the placement of the arrow tail and the arrow head are important. So where should you place the arrow tail? Well, you start the arrow at where the electrons are that are being moved. So it needs to start on a source of electrons. What are some sources of electrons? Well, we have lone pairs. That's a source of an electron pair. You can also start a tail of an arrow on a sigma bond. Sigma bonds contain shared electrons, so that is a source of electrons. And also pi bonds as well are a source of electrons. So we can start on any of those, and we'll talk about radical arrows later, but when you're drawing a single-sided arrow to show the movement of one electron, we would start on the same sort of places it needs to start on a source of electrons, which could also be a single electron. And again, we'll talk about that later. So where should the arrowhead point? Right? Well, it needs to point to where you're showing the electrons will end up. The electrons should end up to form a new lone pair, potentially. They could also end up to show the formation of a new sigma bond, or to show the formation of a new pi bond. And these are all important placements for arrowheads, and we're going to talk about show many examples of how to draw curved arrows. Let's look at a rule before we go. We want to make sure to never exceed an octet for second row elements. Right? Recall that second row elements cannot expand their octet the way third row elements and above can. So they can only ever achieve a maximum of 8 electrons. And sometimes it's very confusing whether or not an arrow is possible, mainly because when we're drawing line structures, sometimes called bond line structures, we don't always show all of the atoms drawn in. So for example, you need to recognize that at this carbon, which is just a little point between these two black lines, there are already 2 hydrogen atoms. We know that because there's no charge associated with this carbon atom, so the carbon should be making a total of 4 bonds. It's making 1 bond to this carbon, 1 bond to the oxygen, which means there are 2 bonds left over to hydrogen atoms. So if there are already 2 bonds to hydrogen atoms and 4 bonds total, there are already 8 electrons at this carbon atom, which means that this arrow doesn't make any sense, and it would violate this rule of exceeding the octet for a second row element. Because if we push electrons the way we're showing here, this arrow shows that the lone pair is being moved to be shared as a pi bond between the carbon and the oxygen. We know it's a pi bond because there's already a sigma bond. So if you're going to be making another bond, it will be a pi bond. Or you can think of it as the formation of a double bond. So if we push electrons to show the formation of a double bond, that would mean that this carbon now would be having 5 bonds because of the 2 hydrogens, the carbon, and now 2 bonds to oxygen. Remember that carbon cannot make 5 bonds. So we cannot draw this arrow. This is considered a bad arrow, right? Because we are exceeding the octet on carbon, which is not possible. So let's take a minute to talk about arrows a little bit more. Some of you may have picked up what I call bad arrow habits from YouTube videos or possibly other instructors. And I just want you to understand what I am looking for when it comes to arrows this semester. Okay, so let's talk about some arrows. So one of the things that bothers me the most, and I see the most commonly, is when people, for example, draw something like this with a negative charge, and then they want to show the oxygen attacking something. Maybe do, for example, an SN2 reaction. So for example, I might draw methyl bromide to do an SN2 reaction. And Commonly, I will see people start their arrow tail on the charge, right, to show the SN2 reaction or the nucleophilic attack from the oxygen, right? So this is a big no-no. Remember the rules for curved arrows. Arrows' tails must start on a source of electrons. The charge symbol is not a source of electrons. I would prefer it if you would draw in the electrons. So for example, it would be much more clear if you drew in all of the lone pairs or non-bonding pairs of electrons and started your arrow in non-bonded pairs of electrons. On heteroatoms, it really makes it much more clear what's happening in the reaction. It would be much better if you started on one of these lone pairs, and it doesn't matter which one. Okay, I'll start on this top one. You can point directly at the carbon. So this is now signifying the formation of a new carbon-oxygen bond or a new sigma bond between the oxygen and the carbon atom. Right? So we've done the proper placement of an arrow because we started on a source of electrons. By pointing directly at the carbon, we are forming the first bond between the oxygen and the carbon, so it must be a sigma bond. The second arrow shows loss of a leaving group. So we'll start on a source of electrons. Again, we've started on this sigma bond, and we're pointing to where the electrons are going. In this case, the electrons are going onto the bromine atom as a lone pair. So I like when you draw in all the lone pairs, it makes it much more clear, and you are following the rules of curved arrows. Let's look at another example, perhaps, of a bad habit. This one is a little bit less common, but still sometimes I'll see it. Let's, for example, look at a tertiary alkyl halide. So it's common to start a mechanism with a tertiary alkyl halide by showing loss of a leading group first. So the proper way to show loss of a leading group would be to start on the sigma electrons between the carbon and the group that's leaving, and then point towards the atom to show that the sigma bonded electrons are forming a lone pair. So this would, for example, form a tertiary carbocation and a bromide ion. And I suppose I should have, oops, this is not the right arrow. Those are just two different ways, the correct way and the incorrect way, right? And then this would form, I should have drawn the products for you. We have formation of a new oxygen carbon bond. And if you want to draw the CH3 here, you can. But remember, with line structures, that's often left out. And then we also formed some bromide ion. That's what formed in that SN2 reaction. Okay, going back to this is the proper way to show the loss of a leaving group with the properly drawn arrow. But how would some people draw this in a way that I would consider incorrect? And that would be if the arrow head is sort of, and sometimes even people will mess up the arrow tail. I've seen things as crazy as stuff like that, right? So this would be an example of an improperly placed arrow tail and an improperly placed arrow head. This did not start on any electrons. It should have started on the bond. And this, by pointing off in space, we don't really understand where those electrons are going. I think they intend to draw this arrow, right, and intend to form these two products of that step. But the arrow is just kind of crazy. They get a little overexcited and point off into space because the bromide is leaving, right? But it's not a properly drawn arrow. So I just wanted to talk a little bit about arrows because it's something that I see when students draw mechanisms sometimes the arrow placement is just less than ideal. Okay. Going back to the slides, I don't know what happened. Got back to the beginning. Okay. All right. So we have moving on to here we go. Okay, so let's talk about resonance pattern recognition. So Klein breaks resonance down into patterns, which I think makes it much easier to learn than trying to learn it without patterns. So the patterns that are described in this book start with the allylic lone pair, followed by the allylic carbocation, lone pair of electrons adjacent to a carbocation, a pi bond between two atoms with different electronegativities, and conjugated pi bonds in a ring. We're going to talk about each pattern briefly in review. So recall that allylic lone pairs are lone pairs of electrons that are on an atom. It doesn't have to be a carbon atom. It could be, for example, a nitrogen atom or other heteroatom. And they are one bond, one sigma bond away from a pi bond. That's how we know that they're an allylic lone pair. And we can move those electrons to every other atom. And it will take two curved arrows to show that electron movement. We'll start on the lone pair with our first arrow. Place the tail of your first curved arrow on the lone pair. Show the electron movement to form, in this case, a pi bond between these two carbon atoms. We know we're forming a pi bond because we already have one bond. We're forming a second bond. But in order to avoid exceeding the octet on this carbon, which by the way has one hydrogen atom attached to it, we need to simultaneously move electrons away from this carbon using a second curved arrow. The second curved arrow starts on the pi bond. So when you have a double bond, we're moving the pi electrons or the electrons in the p orbitals, not the sigma bond. And those in this case are being moved to form a lone pair on this carbon. So we point our arrow directly at the carbon to show the formation of that lone pair. That generates the other allylic carbocation contributor. All of these are examples of the allylic lone pair pattern. You want to be able to recognize when you can draw the allylic lone pair resonance pattern because it's one of the most common patterns that will be used throughout the entire year of organic chemistry. Let's take a look at the charge. When there's a charge on the first structure, for example, a negative charge like you can see here or in this structure, then the second resonance contributor will also have one negative charge. So it's important to remember that with resonance, the charge or the overall net charge should be the same on each resonance contributor. So, and because significant contributors have two charges or less, then when you start with a charge, every structure after that will have that same charge moved to a different location. When you start with something that's neutral and has no formal charge, and you're doing the allylic lone pair pattern, the second structure will have shifted the electrons, which also shifts the formal charge. So now we need to draw both a positive and a negative, which is a net zero charge, which is the same as the net zero charge in the first structure. So we will generate both a positive and a negative charge when starting with something that has no formal charge and doing that pattern. Let's talk about allylic carbocations. Allylic carbocations are similar to allylic lone pairs, except for there's a positive charge at what you might call the allylic position instead of a lone pair. So one bond away from a pi bond, you'll see a positive charge, and in that case, you'll know it's an allylic lone pair. When we're drawing this resonance pattern, we only need one arrow, one curved arrow, and we always shift electrons towards the positive charge with this pattern because electron density will move towards what is electron deficient. So this arrow is showing the movement of these pi electrons, or the double bonded electrons, to shift over to between these two carbons, which then leaves the terminal carbon on the right with a positive charge and electron deficient. And we can keep going. Sometimes if there's an extended conjugated system of p orbitals, so for example, if you have additional pi bonds, what we call in conjugation with the first pi bond, then there will be more than two resonance contributors. We can just shift one pi bond at a time, moving the positive charge to every other atom, as you can see in the three resonance structures drawn here. By drawing, or by using one arrow at a time, we avoid forgetting to draw this middle and also significant resonance contributor. The third pattern is a lone pair adjacent to a carbocation. So when you see a carbocation, sometimes you'll see a pi bond next to it, and that will be the allylic positive charge pattern, but also sometimes you'll see an atom with a lone pair. That lone pair will actually exist in a p orbital, and it will overlap with the p orbital on the carbon bearing the positive charge, which is empty, right? So carbocations possess an empty p orbital, and if there's a neighboring p orbital with electrons in it, they can overlap and those electrons can be shared, and we can draw some resonance contributors which show the sharing of those two electrons. So when we're drawing this pattern, we'll start on the lone pair and we will point to the bond between the two atoms where we're going to form a pi bond. You can see two examples of that on this slide. The fourth pattern is a pi bond between atoms of differing electronegativity. And that's essentially the opposite of the pattern that we just saw, lone pair adjacent to a positive charge. So when you have a pi bond between two atoms and they're not the same atom, so for example, this is oxygen and that's carbon, those are not identical atoms, then we can draw a resonance arrow to show a second significant resonance contributor from that structure. We'll start on the pi bond and we'll move the electrons to the more electronegative atom using an arrow, and we'll form a lone pair on that more electronegative atom, generating the second contributor. So what these brackets in this arrow show us is that these two structures are the two significant contributors, and that the true structure is a hybrid of these structures. Because this is neutral, this is more significant, so the true structure more closely resembles this structure, but the electrons in the carbon-oxygen pi bond actually spend most of their time around oxygen, leaving an electron-rich oxygen atom and electron-deficient carbon atom. So this carbon is actually electron deficient, both through resonance, which you can see here, which just means that the electrons in the p orbitals spend more time around oxygen, but also the electrons in this sigma bond spend more time around oxygen as well. So the electrons in both of these bonds between the carbon and oxygen spend more time around oxygen due to oxygen's electronegativity than carbon. But when we are talking about the electrons in the p orbitals or the pi bond, we call that resonance. When we are talking about the unequal distribution of the electrons in the sigma bond, we call that induction. So those two words, right, mean something different. Resonance refers to the electrons in the p orbitals, and induction refers to the electrons in the sigma bond. Recall that these two structures really represent extreme descriptions of the pi bonded electrons, right? They're not equally shared, nor are they completely unequally shared, right? The true structure is somewhere in between, where the electrons are unevenly shared, but not completely, but still shared and not completely given to the oxygen atom. And the last pattern is conjugated pi bonds in a ring, right? So when we have an aromatic ring like this benzene ring, what we know is that this is not a double bond next to a single bond, next to a double bond, next to a single bond, and so on. Actually, all 6 of these carbon-carbon bonds are equivalent. And they all have a bond order of about 1.5, right? So the only way to truly understand the true structure is to draw these 2 resonance contributors. That helps us to understand that the electrons in the 6 overlapping p orbitals are actually entirely delocalized around the ring and completely shared, right? So that all of these bonds are actually equivalent. And the way we draw those is we use 3 arrows in this case, and we can shift the electrons from the pi bonds to point to the formation of a pi bond on the adjacent carbon-carbon bond. And we need 3 arrows to do that simultaneously to avoid exceeding the octet rule. And you can do this, the electrons can be moved in a clockwise or counterclockwise fashion, and it wouldn't matter either way. Here's a summary of the 5 main patterns. I wanted to mention that with this review video, I'm not going into any practice problems while we're during the video, and that's because you're going to be completing the Organic Chemistry 1 review activity in class, or possibly asynchronously if you're taking an online class. And so you'll be practicing this in that. This is not meant to be a true lecture video. In most of my other lecture videos, however, I will be pausing to do practice problems to emphasize new points. Okay, so let's move to chapter 3, and we're going to start talking about acid-base reactions and using pKa values to predict the position of equilibrium for a reaction. So if you have an acid-base reaction written out, then on the left-hand side of the equation, you'll have the acid and the base. Recall that the acid is a proton donor and the base is a proton acceptor. And in most cases, and that's the Bronsted-Lowry definition of an acid and base. We also briefly last semester talked about the Lewis definition of an acid base, and I won't review that here because we will review it during this semester. Anywho, when those 2 react together, they form the conjugate acid and the conjugate base, where we've essentially just shifted a proton from the acid to the base to form the conjugate acid and conjugate base. Recall that in the reverse direction, if this were to act as the proton donor, it would be the acid. That's why we call it the conjugate acid. Okay, when we're looking at an acid-base equation, what we can do to predict which direction the equilibrium favors is if we have pKa values to use those pKa values for prediction or comparison. And that is water has a pKa of 15.7 and terbutanol has a pKa of 18. So since we know those 2, right, we can determine that the equilibrium will favor the formation of the weaker acid. And that is the one that has the higher pKa value, if you will recall. So it is important to be able to predict the position of equilibrium if you have pKa values. And so I just wanted to make sure that we review that topic. And we know then that the difference of 16 and 18 is 2 pKa units, which means there are 10 to the 2 or 100 more products than reactants in the reaction mixture. Okay, this actually shows the mechanism, right, which is the curved arrows that show the flow of electrons to form products from reactants. So when we're drawing the mechanism of an acid-base reaction, we start on the base's source of electrons, which in this case is a lone pair. And we're going to be picking up the proton from the acid. Recall that we call it a proton transfer, and I say it's picking up a proton because only the nucleus of the hydrogen atom gets transferred. The nucleus of a hydrogen atom is a single proton in the most abundant isotope. And so we say that just the proton is being transferred. The electrons are actually left behind. The electrons in this oxygen-hydrogen sigma bond are left behind on the oxygen as a lone pair, forming, again, the conjugate acid and conjugate base. When we know the pKa values, again, this is a much bigger difference now. We're still using water as the acid, which has a pKa of 15.7, but our conjugate acid in this case is butane. And the hydrogen attached to one of the carbons in butane has a pKa of 50. It's extremely unacidic, or one of the weakest acids you can possibly find. So now there's going to be a huge difference in pKa values between the acid and the conjugate acid. The difference between 16 and 50 is 34. So there's 10 to the 34 more products than reactants, which means there's not much of an equilibrium. Technically, it's an equilibrium, but there's so many more products and reactants that there's essentially no reactants in solution. So oftentimes we'll just draw this single arrow. And we can consider this essentially an irreversible reaction. Okay, I wanted to talk about understanding the difference and being able to predict the difference in acidity of two acids. That's an important topic that was covered in chapter 3 last semester. And we still need to know different structures, different protons, and be able to predict how acidic they are, or if they're more acidic than another hydrogen in the same or different structure, for example. So if we're trying to figure out, is the hydrogen attached to the oxygen atom in ethanol more or less acidic than the hydrogen attached to the oxygen atom in acetic acid, we're actually not going to look at the structure of ethanol and acetic acid directly. Instead, we're going to compare the stability of the conjugate base. The conjugate base can be drawn by just removing that proton, but leaving the electrons behind as a lone pair. That will make the atom have a negative charge in most cases. Right? So this would be an example of the conjugate base of ethanol and the conjugate base of acetic acid, which happens to be resonance stabilized. So what we're really looking at is this more than just the stability of the conjugate base, but the stability of the lone pair left behind after the proton has been removed. And the Klein book utilizes an acronym to compare the stability of different lone pairs on the conjugate base. The acronym that they use is ARIO, which stands for atom, resonance, induction, and orbital. And these factors are in order of importance, the atom being the most significant factor, followed by resonance, and so on. Let's talk about each of those factors so that we can review this acronym and how it's used to predict acidity. So let's look at, for example, if we didn't know the pKa values of butane and propanol, specifically the acidity of the hydrogen shown in red, then we could use this analysis of ARIO to help us predict which one should be more acidic. So the first step to that prediction is drawing the conjugate base, right? So if we remove the proton and we leave the electrons behind, this carbon will have a lone pair and a negative charge, and the oxygen will as well. What we're really going to do is compare which of these two lone pairs is actually more stable. And with the atom, there's two important factors. The first factor is the larger the atom, the more stable a negative charge will be. And this is really important. The size of the atom is the most important factor. But if there's no difference or very small difference, then we'll move to the second factor, which is the electronegativity. So When we use factor number 1 is when we're comparing two atoms that are a very different size, right? Because one is farther down a column in the periodic table. So for example, if we were comparing an oxygen anion versus a sulfur anion, then we're comparing two atoms that have a very different size. Sulfur is a third row element, and so it has a much larger size than oxygen. So we would use this factor. We would say the lone pair on the sulfur atom is much more stable because of the larger size of sulfur than oxygen. But when we're comparing oxygen and carbon, there's not a significant difference in size because they're both second row elements. Instead, what we're going to use is an electronegativity comparison, which is the less important factor than size, but still important if there's not a significant difference in size. What that says is the oxygen atom, which is more electronegative, will be able to stabilize its lone pair more effectively, and as a result, the negative charge, than a carbon atom, because a carbon atom is less electronegative. So basically, it's not able to hold its electrons as close to the nucleus and thus stabilize them as an oxygen atom would be. So if we predict that this conjugate base and lone pair are more stable, then that means that the prediction is propanol is more acidic than butane. Wrong direction. There we go. So again, if we whichever conjugate base we predict to be more stable, then that corresponds to the corresponding acid to be more acidic. And that would match pKa values. Propanol is an alcohol with a pKa of somewhere in the range of 16 to 18 typically. And butane, as we know, this hydrogen we saw before, has a pKa of 50. So it's much less acidic than propanol. So this method of using the atom and comparing size and electronegativity will match the pKa value actual data, which is a good way to predict. Okay, the second factor is resonance. Right? Resonance also stabilizes a lone pair and also the charge associated with that by spreading it out across multiple atoms. Right? So if we wanted to compare the acidity of ethanol and acetic acid, what we're going to do is end up comparing resonance. But that's because the atom is the same, right? So we're not going to be comparing the atom because when we look at the conjugate base of ethanol, which is ethoxide, and the conjugate base of acetic acid, which is acetate, we notice that the lone pair and negative charge are in both cases on an oxygen atom. So there's no difference in the atom. In that case, we then look at resonance, right? And we notice that with the acetate anion, the lone pair is delocalized, which means it's going to be more stable. And if it's more stable, then we predict that acetic acid is more acidic, which is true, right? The pKa of acetic acid is about 5, which is much more acidic than the pKa of ethanol, which has a pKa of around 17. The third factor is induction, right? And induction is, again, the presence of neighboring electron withdrawing groups. And we say that they withdraw inductively because they're withdrawing through the sigma bonding network, not the pi bonding network. So the presence of these chlorine atoms, for example, will play a difference in stabilizing the resulting conjugate base. But of course, the first step is to draw the conjugate base. You should draw the structure of trichloroacetic acid after the proton has been removed, and we've moved these sigma bonded electrons to the oxygen as a lone pair. Same thing with acetic acid, remove this proton and move these electrons to the oxygen as a lone pair. When you're comparing the two conjugate bases, right, then you'll notice that the chlorine atoms are able to pull some of that extra electron density away from the oxygen with a negative charge, or in this case, the two oxygens that share the negative charge towards it, helping to stabilize it. So if the conjugate base is more stable, then we predict that acid is more acidic. The fourth factor is the orbital, right? And so this one is only considered when there's no difference in the atom with a negative charge. There's either no difference in resonance or there's no resonance stabilization of the lone pair, a negative charge. There's no nearby electronegative atoms, which would cause a difference with induction. In that case, we can look at the orbitals. So let's review some orbitals that a lone pair might be in, right? It might be in a sp hybridized orbital, an sp2, or an sp hybridized orbital. And the shape of those orbitals is very different, right? The sp orbital has more s character. In fact, it has what we call 50% s character because it's made up of one s and one p, so 50% from an s orbital, which means it's going to more closely resemble an s orbital, which is a spherical orbital around the nucleus. So it's a little bit shorter, and thus the electron density in here would be closer to the nucleus than, for example, it would be in an sp2 or an sp3 hybridized orbital. So let's say we were comparing the acidity of the proton here drawn in blue and the one drawn in red. Of course, the first step is drawing the conjugate base. So in this case, we have the lone pair and negative charge on the carbon here on the far left versus the sp hybridized carbon on the far right. So this one is sp2 and this carbon is sp3. And the lone pair is in one of those hybridized orbitals. So this lone pair is in an sp2 hybridized orbital. This lone pair is in an sp hybridized orbital. Recall that the electrons are more stable when they're closer to the nucleus, and they are closer to the nucleus in sp hybridized orbital. So since we would predict these electrons are more stable, that means that this corresponding proton in blue is more acidic. And that does match pKa values. The pKa of this proton in blue, right, which is a proton attached to a carbon that is participating in a triple bond, is about 25, and the pKa of the proton in red is about 44. So that way, our prediction matches the data. Right? Again, so the lone pair in an sp2 hybridized orbital is not as close to the nucleus, so it's less stable than a lone pair in an sp hybridized orbital because of the shape. The electrons get closer to the nucleus, predict they're more stable, which predicts this is more acidic. And again, those are the two pKa values I was talking about, 25 versus 44. And if you are looking at a hydrogen attached to an sp3 hybridized carbon, and again, there's nothing nearby to help make this more acidic, like some resonance or induction or something, then it would just have pKa of 50, which is on the high end of the pKa values, meaning it's not acidic at all. Okay, so it is important to recognize that ARIO is only a guideline of priority, and it sometimes fails. If you want to know the true prediction, then you do need to have the pKa values, which a lot of times can be looked up in a book or on the internet. So if we were to do a prediction in this case, right, we would be looking at the stability of the base and the conjugate base. Just recall, when we're making our predictions, we don't really compare the two acids, right? In this case, it would be the acid and the conjugate acid. We compare the conjugate bases of those two acids, which in this case are the base on the left-hand side and the conjugate base. We're really comparing the stability of the lone pair on this carbon atom versus one of the lone pairs on the nitrogen atom. Nitrogen and carbon are in the same row of the periodic table. So we would predict that nitrogen, being the more electronegative atom, should be able to stabilize its lone pair better than carbon. And as a result, this should be more stable, which would predict that the acid would be more acidic. But that actually does not follow the pKa values here, right? We have this prediction that ammonia should be more acidic because this is more stable, nitrogen being more electronegative than carbon. But it's not true. Ammonia is actually the less acidic of the two. You can see here the pKa value is higher. It's 38, not 25, or versus 25. So this did not, this REO prediction failed in this case. And that's just because with a small difference in electronegativity between nitrogen and carbon, it's not as dominant a factor in this particular case as the difference in the orbital, right? This lone pair is sp3, and this one would be an sp hybridized orbital. So in this case, the orbital is actually a more dominant factor than the atom, just because of the two atoms that are in question, nitrogen versus carbon, which is not a large difference in electronegativity. And there's a very big difference between an sp3 hybridized orbital and an sp hybridized orbital. But REO tells us to use these in order, and the atom is more important than the orbital, which actually doesn't match the what is truly thought about this. So it's just important to recognize that there are sometimes exceptions to REO, and that if we have pKa values, that is the true data that we can look at, right? And you notice that there's a huge pKa difference between the acid and the conjugate acid, a difference between 25 and 38 of 13. So there's 10 to the 13 more product reactants, and they're actually just using a single arrow because they're considering this reversible. So Klein considers anything with a pKa difference of 10 or more to essentially be irreversible. Okay, moving on to topics from chapter 4. I wanted to review drawing Newman projections. We won't use Newman projections a lot in second semester, but we will use them a little bit, and this topic could come up on your final because you're taking the American Chemical Society standardized final over the entire year of organic chemistry. So some topics from first semester may also show up on that exam. So it's good to review this topic. So recall that when we're drawing a Newman projection, we're placing our eye to look down a certain bond. Usually it's a carbon-carbon bond, but it could be other types of bonds as well. And when we're drawing the Newman projection, the front carbon is just this little dot, right? And the back carbon is represented by this circle. And the reason it's represented that way is because in reality, the back carbon is completely eclipsed by the front carbon. So you wouldn't be able to see it at all. So in order to be able to see it and understand the groups that are coming off of that atom, we actually draw it as a circle and instead of being just directly behind this dot. So we see that this hydrogen in red is pointed straight down with respect to the observer looking down the bond in this direction. And so then that would be this hydrogen atom that's pointed directly down here. And then one of these hydrogens is on a wedge and one of them is on a dash. Those are the two hydrogens off to the left and right with respect to this person's perspective. As they look down this bond, there are groups attached to the back carbon. For example, this hydrogen that's pointed straight up, that's going to be the one that's directly opposite the hydrogen that was pointing straight down on the front carbon. And then we have these two, which would be on a dash or a wedge, which they haven't really shown. And that's just because it doesn't matter because they're both hydrogen. Let's look at another example, right? In a case where all of the groups are not hydrogen atoms. Let's say we were drawing a Newman projection by looking down this carbon-carbon bond. This will be the front carbon, and it has a methyl group pointed straight down, and it has two hydrogen atoms off to the left and the right. So we have the methyl group pointed straight down on that front carbon, and the two hydrogens off to the left and the right. Looking down this carbon-carbon bond, we come to the back carbon. Pointed straight up is a chlorine atom. So notice how they have that pointed straight up and completely opposite the methyl group on the front carbon. And then in this case, this is a chiral center. So we have a methyl that's pointed back, right? And a hydrogen that's not shown, but it would be on a wedge here, right? So from this person's perspective, the group that's behind the plane is on the dash, right? That is sort of off to the person's left, and the group that's coming out of the plane, the hydrogen, is to the right. So notice that they draw the methyl off to the left and the hydrogen to the right. So this actually is important not to switch the methyl and hydrogen. That would be drawing the enantiomer of the structure and not the correct structure. Okay, I actually just have a blank slide for drawing chair conformations because it's easier for me to just freehand draw chair conformations just as a little review for you guys. Okay, so let's go ahead and draw in some, let's see if I can get this a little blurry. There we go. That's better for you guys. Okay, so when drawing a chair conformation, right, so what we're going to do is we draw those for cyclohexanes. Drawing a cyclohexane. And let's go ahead and put some substituents attached to that as well. So maybe there is an up chlorine, and then maybe 2 carbons away, we have a down hydroxyl group. Right next to that, we'll have another down, just methyl. So I'll just leave it. Okay, so when we're drawing the 2 chair conformations, right, we want to draw the chair first. And the way I started is I draw 2 parallel lines. So sort of going, I can start with going down and to the right. And I want the top line to be a little bit higher up on the paper than the bottom line. So I've got these 2 parallel lines, and then 90 degrees from those 2, I'll draw 2 more lines. And then we're going to connect those 2 with another set of parallel lines. That is one of the chair conformations. And then what I want you to recognize here is that when you're drawing a chair conformation, when you see something that's on a wedge, we're going to call this up, right? And when you see something that's on a dash, these 2 are down. And no matter which chair conformation you're drawing, the chlorine needs to be in an up position, and the hydroxyl group or the alcohol group and the methyl group needs to be in a down position. So, and I can start anywhere. Like I can place this chlorine at any single carbon I want to, right? As long as I'm then move consistently in a clockwise direction, for example, to place the other group. Let's say I want to place it on this carbon. I need to place it in an up position. So the up position is the axial position. And I'm going to draw in all of the other hydrogens as well. So the down position in this case would be equatorial position. But the chlorine here is in up position. So when I say up, it just means that it's farther up. So this is higher up than that one, as it's drawn on the page. So this is the up position. Notice that we just have hydrogens here. So we can just draw in both of those hydrogens. We have the hydrogen that's equatorial and the hydrogen that's axial. By the way, this is the up position of that carbon. This is the down position of the carbon. Moving on to the next one, sort of in a clockwise direction, I have reached this group here where now I have the OH group in a down position. So the down position of this particular carbon is the equatorial position, which we're going to draw parallel to this line and this line. There, so that will be the OH group. And then there's also up hydrogen in that carbon. Now we're at the down methyl, right? So down at this position is the one that's further down, which happens to be axial position. So methyl here. And again, you could write CH3 in if you wanted to, or just leave it as a regular line. Okay, so yeah, just for clarity, I'll go ahead and put CH3. So it is at the down and axial position. And there's also up equatorial hydrogen of that carbon. And then moving up here, these are just two what we call methylenes, CH2 groups, right? And so they both have two hydrogens attached to them. So we have both up and down and axial and equatorial hydrogens. Right, so this is one of the two chair conformations, and it can also flip to the other chair. So let's practice drawing the other chair as well. So notice, remember when we started drawing this structure, we went down and to the right, and with the top line being a little bit higher up, right? So we sort of want to go up and to the right now to draw the other chair conformation. Right, so sort of, instead of going down and to the right, I'm going up and to the right. And again, I just want to make sure that the line that's higher up goes a little bit higher up. So I draw this one and that one, right? So, and this is a little bit, higher up than this one, so I know I've done it correctly. Again, my 90-degree angle lines from there, and then connect those. And we want to then figure out where the carbons are going to be after they remove them. I'm just going to make a little circle on this one just so we can identify it. So this carbon sort of flips down in a chair flip. So it's going to be this carbon. Then we'll know all the other carbons by reference. Okay, the chlorine still needs to be in an up position, right? Right now it is in this chair, it's up and axial. So when it flips, it's going to be up and equatorial. So it is going to be right here, up, right, and equatorial. And then the down hydrogen becomes axial. And as we're moving, again, we have just a methylene here. So we sort of straight up for the axial position. Make sure it's parallel to that line for the equatorial position. Then we've moved to the carbon with the OH group. That OH group needs to be down. Right now it's down in equatorial and it's going to flip to down and axial. Okay. And then the hydrogen, which was up in axial, is now in equatorial. Next we have the down methyl. This carbon down position is equatorial. And it's flipped from down and axial to down and equatorial. The hydrogen up here, and I'm just going to go ahead and add in the rest of the hydrogens, both axial and equatorial for the other two methylenes. Now you don't have to draw in all the hydrogens unless you're asked to. I just wanted to do that to remind you what that would look like. Okay, so we have the two different chair conformations here, right? Notice that in both chair conformations, the chlorine is always up because it's on a wedge. The hydroxyl group and methyl are always down because they're on a dash, but they do switch from equatorial to axial and vice versa. Okay, moving on to chapter 5, we're going to be talking about isomers. And we're first going to start off with remembering that isomers are different compounds that have the same molecular formula. And there are two general types of isomers. There are constitutional isomers and stereoisomers. Constitutional isomers have different atom connectivity. So these two structures actually have the same molecular formula. Right? It is C4H8O. Both have that same molecular formula, but the atoms are connected in a different way, and that makes them constitutional isomers. And they look very different, so it's hopefully fairly easy for you to pick them out compared to stereoisomers. Stereoisomers actually have the same molecular formula, and the atoms are attached in the same general arrangement. So all the atoms are attached to the same atoms. The difference is in the spatial arrangement of the atoms. So the 3D structure is different with stereoisomers. And for example, right, these, you might recognize these two as mirror images, right? Those are what we're going to call enantiomers, which is a type of stereoisomer. And then these two structures, which you might recognize as cis and trans. Right? And cis and trans are a type of diastereomer, which is a type of stereoisomer. And the reason why these are not the same structure is because it is impossible to rotate the double bond. And so these structures are actually two different structures that are unable to interconvert. Okay, so within stereoisomers, as I've been talking about, there are subcategories, which are enantiomers and diastereomers. And simply, enantiomers are two structures that have the same molecular formula. So they are isomers. They have the same atom connectivity. So they are stereoisomers, but they do not have the same 3D arrangements in space. And specifically, the two structures are non-superimposable mirror images, which makes them in the classification of enantiomers. If the two structures are not related as mirror images, then they are grouped into the diastereomer category. It's important to be able to designate a chiral center, also known as a stereocenter, as belonging to the R or S configuration. So let's practice that. Okay, so when we are designating the R and S configuration, the first thing I like to do is draw in all of the groups that are at the chiral center. So this is a chiral center. And what we see is 3 groups, but we also have a hydrogen that's coming out at us, right, that we need to consider. So when next we need to prioritize the groups. And we prioritize based on what atom is directly attached to that chiral carbon. So for example, that carbon has a hydrogen, a nitrogen, and 2 carbons directly attached. And then we look at atomic number. Whichever one has the highest atomic number has the first priority. So nitrogen has a higher atomic number than carbon and hydrogen, so it gets the first priority. Next would be 2 carbon atoms, right? And those have an equal atomic number because they're both carbon. But when we look and see what's attached to those carbons, this carbon has 3 oxygens attached, and this carbon has a carbon and 2 hydrogens attached. So this has a higher priority because oxygen has a higher atomic number than carbon and hydrogen. The other carbon would be priority number 3, and then the hydrogen is priority number 4 with the lowest atomic number. So we've prioritized the groups as 1, 2, 3, and 4. And then we need to draw a line or in sort of a circular arrow to go between 1 and 2 and 3, ignoring 4. So just starting on 1, and move to 2, and move to 3, and we draw a little arrow here. This is not, by the way, signifying the movement of electrons. This is just trying to figure out if it's R or S. So with a clockwise motion here, right? Normally clockwise would be R, except for the fact that our 4th priority group is pointed out at us. We're actually looking at it from the wrong direction. We should be looking at it sort of from behind the paper, not in front of the paper. And so if we're looking at it from behind, what from our perspective looks like clockwise, the other perspective would look like counterclockwise. So this is action F. So clockwise directionality of our arrow with the 4th priority group coming out at us means that it is S. And let's go over here and look at this example, second example. Now we want to look at this carbon, right? It's a chiral center, and it has oxygen, chlorine, carbon, carbon attached. So in terms of atomic number, chlorine has the highest, Oxygen has the next highest atomic number, and then carbon and carbon are a tie. So because we have a tie, we're going to look at what's attached to those carbons. This carbon has carbon, carbon, and one hydrogen attached. This one has carbon and two hydrogens attached. So this one is going to have the higher priorities, and then this is group 4. So notice that in this case, we have a situation where our 4th priority group is actually not on a dash or a wedge, but instead in the plane. Right? So there's a variety of strategies you can use to determine the RNS configuration. But one of those strategies is to just switch groups, right? So I could, for example, redraw this. There's my chiral center. And I'm going to sort of draw the wedges where the wedge is. Right? Draw the dash where the dash is, and then draw the two in-plane lines where they are. Sort of start at that place. Now I'm going to switch groups. And what I want to do is switch the 4th priority group with whatever is in the back. The reason I want to do that is because ideally I want my 4th priority group in the back. Right now it's in the plane and the chlorine is pointed back, but I want my 4th priority group in the back. So I'm going to switch it with the chlorine so that it can be in the back, which would mean now the ethyl group here, which is our 4th priority group, is in the back, and I'm going to place my chlorine over here. So I've switched those two groups. If you leave the hydroxyl group in place and leave the isopropyl group in place, let's say you were to get R here, that means that the structure would be S, because when we switch two groups, we switch from R and S. So if you want to get the same priority as the original, meaning if I figure out this is S and that will also be S, then I need to switch two groups and switch the other two groups as well. So optionally, I can also switch the hydroxyl group and the isopropyl group, right? And now, because I have switched two groups and switched the other two groups, whatever R and S configuration I get here, it will be the same up here, and I won't have to remember to switch it. The priorities are still the same, right? So it's still 1, 2, 3, and 4, just as we had figured out before. But now it's much easier because my 4th priority group is in the back where I ideally want it to be. So I'm going to draw a line from 1 to 2 to 3, 1, 2, 3, ignoring 4, right? Notice that I have got a clockwise directional arrow here, which means that this is R, and I don't have to switch it because my 4th priority is in the back where it's supposed to be, which means that this one is also R. Right? I know that they're both R because I switched two groups and I switched another two groups. That's like when I switched two groups, it went to S, and when I switched the other two groups, it went back to R. Hopefully that makes sense to you. You can always let me know if you have any questions. Okay, let's talk a little bit about symmetry and chirality. So when you have a structure that has an even number of chiral centers, so 2, 4, 6, etc., it's possible that that structure has an internal plane of symmetry. Right? You can see here that we're slicing this right in half. So there's this, and the two sides are symmetrical. Right? So when you have an even number of chiral centers, so both of these, by the way, are chiral centers. There's 2 chiral centers in the structure, and you have an internal plane of symmetry, then the structure overall is actually not chiral. We call that achiral. And this structure is known as a meso compound. Right? Meso compounds are compounds that are achiral overall, not chiral overall, but have chiral centers in them, and they have to have an even number of chiral centers, and such that the chiral centers are actually opposites of each other through that internal plane of symmetry, and one chiral center sort of cancels out the other one, and overall the structure isn't chiral. Let's talk a little bit about Fisher projections. Fisher projections are a way to represent structures. They utilize sort of cross here for having 4 groups attached. The center carbon here is often a chiral center. It will be if there's 4 different groups attached. And what's important to recognize is that the horizontal groups, which again are the hydrogen here and the OH group, those are coming out of the plane on wedges. And the ethyl and methyl group, which are on the vertical line, are actually pointed back. So if we have this, understanding gives us stereochemical information. So for example, because this is a chiral center with 4 different groups attached, we should be able to figure out if this chiral center can be designated as R or S. And we can do that if we have information about the wedge and the dash situation, right? So we have, and you can place these, but directly attached to this carbon is oxygen, hydrogen, carbon, and carbon. Oxygen with the highest atomic number will be priority 1. Hydrogen is priority 4. Carbon and carbon is a tie. And the ethyl group with an additional methyl attached to the carbon directly attached to the chiral center will have a higher priority. So we'll write in a 2 and a 3 here. So again, we're going to draw our line from 1 to 2 to 3, ignoring 4. And we have, again, a clockwise directional arrow. But one of the things we want to remember is that our 4th priority group is actually on a wedge or coming out at us. So remember that when that happens, we have to switch it. Right? So clockwise in that case is actually S, and that chiral center is actually S. Okay, so here are some additional structures that have been drawn as a Fisher projection. These are all sugars, and sugars are commonly drawn in Fisher projection because they have a series of consecutive chiral centers. And it's easy to represent those chiral centers using a Fisher projection. So we want to recognize that this structure has 2 chiral centers, right? 3 intersections means 3 chiral centers, and then 4 chiral centers. Let's talk about E and Z designations for alkenes. Sometimes you can classify alkenes as being cis or trans, and sometimes it's not possible to classify as cis or trans, and we need to use a different designation system. In that case, we would use an E or Z. So when we're doing the E and Z designation, what we're going to do is look at the 2 carbons that are sp2 that are participating in the pi bond. And we want to look between these 2 groups, which one gets priority. Priority is determined just like R and S. It's whatever has the higher atomic number. And if there's a tie, you keep going until you find a point of difference. So in this case, we're comparing fluorine versus carbon. Fluorine having a higher atomic number gets priority. On the second sp2 hybridized carbon, we're comparing nitrogen versus hydrogen. Is what's directly attached. Nitrogen having a higher atomic number gets priority over hydrogen. So the 2 groups with priority are the fluorine and the nitrogen, shown here in red. When your 2 priority groups are on the same side of the pi bond, we call this Z. And if they were on opposite sides of the pi bond, we would call that E. It's important to recognize that you can have an alkene that is considered trans, but also Z. So normally people think of, and it's true for the majority of cases, that if you had a trans double bond, it would be an E double bond. But because cis and trans is determined differently than E and Z, it's possible for example, something trans to be Z or something cis to be E. Let's look at an example of that. See, this one, we actually cannot classify it as cis or trans because cis or trans is defined by identical groups being on the same side or opposite side of a double bond. So for example, we have this structure here, which has two identical methyl groups. They are on the same side of the double bond, so we would call this cis, right? And the methyl also has priority over the hydrogen at this carbon. Again, this methyl has priority over the hydrogen at this carbon. And so the two methyls are the highest priority groups. And so we would also call this Z, right? So this is a cis or Z double bond. This particular alkene doesn't have identical groups. It has four entirely different groups. So we cannot call this cis or trans. But in some cases, we could call something cis or trans or E or Z. Let's look at another example. Right? What if we had a structure like this? How would we classify this? Well, if we look at the identical groups, those are the two methyl groups. Those are on the opposite side of the pi bond. So we would actually call this trans. Right? But if we look at the priority, so carbon versus fluorine, which one gets priority? Right? Fluorine gets priority because it has a higher atomic number than carbon. Methyl versus hydrogen here. Methyl, having a carbon directly attached, gets a higher priority than hydrogen with a higher atomic number. So the methyl on this carbon and the fluorine on that carbon are the two priority groups. Those are actually on the same side of the double bond. So this can be considered trans or Z. So notice that cis and trans doesn't mean E or Z, right? They are determined using different rules. So it's possible to have any combination. Okay, moving on then to chapter 6 and kinetics versus thermodynamics. This is an important point that will come up several times in organic chemistry too. So if we have a pathway, right, where we have reactants or even an intermediate in the reaction that is identical, and then it can go off into two different paths, forming different products, for example, C plus D or E plus F, then it's possible that there's a situation where there is a pathway that has a lower activation energy, right? Recall that the activation energy is the difference between the starting energy and the energy at the transition state. So there's a pathway that has a lower activation energy, but produces less stable or higher energy products than a second pathway, right? So there have the red pathway. We would call this the kinetic pathway because E and F are formed faster due to the lower activation energy. And at low temperature, major product would be E and F. And the reason why that works at low temperature is because again, E and F form faster, and that happens at any temperature. But at low temperature, there's less likely for there to be enough energy for the products to go back to the reactants, right? So if some of them go over the higher energy pathway and get to form products C and D, at low energy, there's a lot less, low temperature, excuse me, there's a lot less energy available, and there's a lot less likelihood that the reverse reaction with a much higher activation energy in reverse will be able to be possible. And if the reaction is not reversible, then we don't form an equilibrium between the two pathways. So whatever forms faster is trapped as the major product. So at low temperature, E and F would be the major product, and we call that the kinetic favored product, or products in this case. But what happens at higher temperature, right? If the reaction is run at higher temperature, still initially more reactants, A and B, will have enough energy to overcome the lower activation energy pathway and form E and F. So initially, the concentration of E and F in solution will be higher. But at high temperature and given enough time, then it's much more likely that the reverse pathway becomes feasible and there's enough energy to go back. And if there's enough energy to go in both directions, eventually an equilibrium can be established, and the more stable product will be the major product. It will have a higher concentration at equilibrium. So we call this the thermodynamically favored products. So temperature can affect product distribution when there's multiple products that can be formed if there is a set of product or products that is favored kinetically and different products that are favored thermodynamically. And again, that's an important topic, but we will continue to discuss it as we go through organic chemistry too. Okay, chapter 6 also talks about nucleophiles and electrophiles. So it is super important that we understand not only what entire substrate is considered the nucleophile or the electrophile in a reaction, but also the carbons or atoms involved, specifically what atom is considered nucleophilic or electrophilic. So first of all, when we have an atom that has either a full or partial negative charge, it is electron rich, right, and considered nucleophilic, and it is attracted to things that are positively charged. If you have an atom, for example, a carbon, but it could be a different atom as well, that has either a partial or a full positive charge, it is electron deficient and it is attracted to electron rich. And if it's electron deficient, we call it electrophilic. Right? So with chlorine, which is more electronegative attached to carbon, the carbon is electron deficient. But when carbon is attached to lithium, which is less electronegative than carbon, then the carbon actually has more electron density around it and a partial negative charge, and this is nucleophilic, right? So it's important because understanding what is nucleophilic and what is electrophilic will allow you to understand which things are likely to react in a mixture. Here are some examples of different nucleophiles. Again, they tend to have either a full or partial negative charge. As a result, they can donate a pair of electrons. They are considered Lewis bases, right, which means they donate an electron pair. And the more polarizable the atom is, the more nucleophilic it is. Polarizable refers to size. So the larger the atom, for example, we don't see any up here, but if we had a sulfur atom with either a negative charge or even neutral, it's actually a strong nucleophile because sulfur is a much larger atom. And that makes it more polarizable, which means it can distort its electron cloud more easily and thus donate that electron density to an electrophile. Even pi bonds are considered nucleophilic. Specifically, we're referring to the two electrons in the overlapping p orbitals, or the electrons in the pi bond. Those are weakly held electrons compared to sigma bonded electrons. And as a result, structures are able to donate those electrons to other structures more easily, and they are considered nucleophilic, even without a negative charge. Okay, electrophiles, again, are electron deficient species. They can accept a pair of electrons. So they either have a full or partial positive charge. That positive charge can be the result of induction alone, as is the case in this alkyl halide, where the chlorine is pulling electron density through the sigma bonds. We call that induction towards it and away from the carbon, leaving a partial positive charge. Or it can be the result of both induction and resonance, as in the case of this carbonyl. Both the pi and the sigma bonded electrons in the carbon-oxygen double bond spend more time around the oxygen than the carbon, leaving a partial positive charge on this carbon and making it electrophilic. Electrophiles are Lewis acids, which means they're electron pair acceptors. And carbocations are a great example, and positively charged carbons are great examples of, partially positively charged carbon atoms are great examples of electrophiles. But they don't have to be carbon atoms. It could be a partially positively charged sulfur atom, for example. Okay, let's talk about curved arrows to show how electrons move as bonds break and or are formed. Right? We talked about this before when we were talking about acid-base reactions, which are proton transfer reactions. And we use two arrows to show the electron movement here. But there are other types of or ways that electrons can move in polar reactions that are not just a proton transfer. We also have nucleophilic attacks, loss of a leaving group, or rearrangement. So there are 4 patterns, including proton transfers as one of the patterns. And it can be really helpful when drawing mechanisms to understand what is happening in each step. Is it a nucleophilic attack? Is it the loss of a leaving group? So that you can sequence steps in a way that shows an entire mechanism. Let's talk about each of these patterns in review. So a nucleophilic attack is when a nucleophile or electron-rich species, we say it attacks, but basically it means it's forming a bond with an electrophile or sharing an electron pair with an electrophile. So we start our arrow on a lone pair or a source of electrons on the nucleophile. Again, it could be a sigma bond or a pi bond. And it is going to point directly at an atom if it wants to signify the formation of a sigma bond with that atom. And thus we have a reaction that has generated a new product. The electrons, because they're going to be part of the sigma bond, are shared and not transferred. Here's another example of a nucleophilic attack that's a little more complicated than the one on the previous slide. Specifically, we are attacking the carbonyl carbon of this acyl halide, which is one of our functional groups that hopefully you're studying. And in this case, we need to use 2 arrows to show this nucleophilic attack. And the reason is the oxygen, which has a partial negative charge and is nucleophilic, can use one of its lone pairs to form a sigma bond with the carbon, but it cannot do that and without something else happening at the same time, because that would violate the octet of this carbon. Remember, we cannot form a 5th bond to carbon, and this carbon already has 4 bonds. So simultaneous to that nucleophilic attack and that formation of the new sigma bond between the oxygen and this carbon, we also need to have electrons being moved away from the carbon. So we can move, it's easy to move pi electrons away, right, from the carbon, especially because it's bonded to an oxygen. And we know those electrons in that pi bond spend more time around the oxygen anyway. So formally, we're moving them to the oxygen, right? But they were really mostly there already anyway. So we can think of this as a nucleophilic attack arrow to form a new sigma bond and a resonance arrow to move electrons up to the oxygen. And the reason we can think of it as a resonance arrow is because it's one of our resonance patterns. Recall pi bond between atoms of differing electronegativity, right? We can draw a resonance arrow for carbonyls that show the pi electrons as a lone pair around the oxygen instead of being shared between the carbon and oxygen. So if you wanted to, you could even draw this as 2 steps. You could draw the resonance separately in first, showing the positive charge that results on the carbon, and then the nucleophilic attack to form the new carbon-oxygen bond. But because it takes more work to show 2 steps with resonance being drawn out separately, it's very commonly done at the same time. Here's another example of a nucleophilic attack. Recall that pi bonds can also act as nucleophiles because they're weakly held electrons. We can actually start an arrow on a pi bond, and then that basically shows that those 2 electrons in that pi bond are being used to form a bond to this sulfur atom. And we need to move electrons away from the sulfur at the same time to maintain the same number of bonds. But notice that this sulfur is making 6 bonds, and that's totally okay because it's a 3rd row element and it has an expanded octet. When we use a pi bond as our nucleophile, only one of the 2 atoms that participate in the pi bond can get the new sigma bond to the electrophilic atom. The other one becomes positively charged because it's now electron deficient, because the electrons that were shared as a pi bond are now moved away from that carbon, leaving only 6 electrons and as a result, a positive charge. Let's look at the second pattern, loss of a leaving group. That is oftentimes considered the opposite of a nucleophilic attack, where instead of forming a bond, we're breaking a bond. And we're doing so what we call heterolytically, which means we're moving 2 electrons during that bond breaking process. And the arrow starts on the sigma bond. Those electrons, instead of being shared, are going to be transferred to the bromine as a lone pair. As a result, we now have 2 species as the product, the tertiary carbocation and the bromide ion. It is also common to show more than one arrow for the loss of a leaving group step. Technically, this entire set of arrows is loss of a leaving group along with resonance. The actual loss of a leaving group is the bond breaking between this carbon and chlorine, where the chlorine is leaving as chloride, which would result in a positive charge of this carbon once the chlorine or chloride has left. But that's not going to be the most stable resonance contributor. So instead of drawing it, oftentimes we can draw other curved arrows, which are essentially just resonance arrows, to then draw the most stable resonance contributor directly. Sometimes people like to think of this as the oxygen is helping push electrons, right, through a series of overlapping p orbitals to help the chlorine leave or get kicked off. The third pattern are proton transfers. And these are, again, just the transfer of the hydrogen's nucleus from one species we call the acid to the other species, which we call the base, right? And we need a minimum of 2 arrows to show proton transfers. And here are some examples. Sometimes we call them protonations versus deprotonations. And that refers to whether or not the organic substrate, which is the substrate of interest in organic chemistry, is gaining or losing a proton. When it gains a proton, we say that our substrate was protonated. When it loses a proton, we often say the organic substrate was deprotonated or lost a proton. So if we show, for example, a water molecule coming to pick up this proton and deprotonating our substrate, getting us back to the carbonyl, we would call this a deprotonation. Sometimes we don't know exactly what species in the reaction mixture is taking the proton. And so sometimes we won't show the base, right, coming in to take the proton. We'll just show the proton leaving, essentially like it's going off in solution, or it can be attached to some base somewhere, and we're just not specifying it. So this is a way of showing a deprotonation without really specifying what exactly was the base that came and took this proton. Instead, it's sort of just, we know it leaves the substrate of interest, and that's the only thing we care about. Here's another example of a proton transfer. In this case, you can see there's 3 arrows used instead of 2, and that's because they're combining it with resonance, and that's very common. So if we, there's 2 ways to show the hydroxide coming in to deprotonate this proton. Optionally, you could show the hydroxide's lone pair picking up the proton and the electrons from the carbon-hydrogen bond being transferred from the sigma bond to a lone pair on the carbon. And then separate to that, you could show an allylic lone pair resonance pattern to get up to this second resonance contributor. These 3 arrows actually combine this entire process into one step. So as the hydroxide, which is the base, comes in and takes the proton from the organic substrate, instead of delivering the sigma bonded electrons as a lone pair on the carbon, instead we can shift them over to form a double bond between the carbon and carbon. See here. The only problem with that is we can't make a 5th bond to carbon, and this carbon already has 4 bonds. So at the same time, we also need to shift these pi electrons up to the oxygen to show 3 lone pairs on oxygen. So it's essentially a way to get all the way from the hydroxide and the ketone substrate to the more stable, more significant resonance contributor in one step. Rearrangements. Rearrangements are common steps when you have carbocations that are formed in a reaction mixture. And we want to talk about sort of why rearrangements happen and be able to show a rearrangement in a mechanism and predict when it's going to happen. Those are all important things to know about rearrangements. First of all, let's look at a carbocation. Again, remember that a carbocation is a carbon with a full positive charge, and it has only 6 electrons around it, so it's very electron deficient. It does not have an octet. And it has an empty p orbital, right? So this is a p orbital with no electrons in it. And if it happens to have a neighboring carbon that has bonds, then it is stabilized by a term we call hyperconjugation. So let's draw that out. This methyl group, right, has a carbon with 3 bonds to hydrogen. So there's 2 hydrogens just drawn regularly. And then this is the 3rd bond to hydrogen, where they happen to have drawn in the orbitals involved in forming the sigma bond. This carbon is sp3, so it is using an sp3 hybridized orbital, overlapping with hydrogen's 1s orbital to form the sigma bond between the carbon and hydrogen. And it just so happens that this set of overlapping orbitals forming a sigma bond can align or be in the same plane with the empty p orbital. And if it's right next to the empty p orbital and in perfect alignment with it, then electrons that are in this space from the sigma bond can be donated into that empty p orbital, helping to stabilize the carbon, making it not as electron deficient. That's what we call hyperconjugation. And this is important to understand for rearrangement, because when you see this picture, it makes it a little bit easier to understand why hydride shifts, which are a type of rearrangement, occur in the first place. So if we have this carbon-hydrogen bond with electrons in it, right, since it's already overlapping with the p orbital, it's possible for the hydrogen and the 2 electrons in the bond to sort of just jump right over to the p orbital. And it can essentially jump over here, leaving this carbon electron deficient. So because they're already overlapping and aligned, it makes sense that the electrons can sort of just, instead of being associated with this carbon, they could sort of shift over to an adjacent carbon. And that's what's happening in a hydride shift. Let's talk a little bit about carbocation stability. It's important to recognize that because of increased hyperconjugation, the more substituted a carbocation is, the more stable it is. So a tertiary carbocation is the most stable because it has 3 R groups, which means that it has triple the hyperconjugation, right, occurring to help stabilize the empty p orbital on that carbon. And structures that have less stable carbocations, for example, secondary carbocations, there's a driving force for those to rearrange to become tertiary carbocations because tertiary carbocations are more stable. Typically, methyl and primary carbocations are too unstable to form. They're too high in energy, so the activation energy to get to those sort of intermediates is very high. And as a result, they are less likely to form in a reaction mixture, so we don't draw those in mechanisms. Okay, so what you'll see here are 2 examples where there's a secondary carbocation. Those actually do form, they're stable enough to form, so it's okay to draw them. If it happens that you have the ability to shift a hydride over, right? We call this a 1,2 hydride shift because it's coming from, this was carbon number 1, the hydride is coming from the adjacent carbon of carbon number 2. So again, because there's overlap of the empty p orbital and the bonding orbitals, then there can be a shift, right, between where the hydride, and remember, it's not called a proton transfer, a proton shift, because more than just the proton is shifting. The proton in the hydrogen's nucleus is shifting, but also the two electrons are shifting as well. So we call it a hydride shift because it's hydrogen and two electrons. Hydrogen with two electrons and a negative charge is called hydride. It's a hydride shift, and it occurs because we've gone from secondary to a tertiary, more stable carbocation. Also, we can have what is called a methide shift, a 1,2 methide shift. So if there's a methyl group on an adjacent carbon, then that can also shift over as well, and the electrons come with it, right, leaving the more stable carbocation as a result. So we can do hydride or methide shifts, but those shifts can only come from adjacent atoms, and it only happens if the carbocation becomes more stable as a result of that shift. Let's talk about multi-step reaction mechanisms, right? So oftentimes in last semester, you were asked to draw mechanisms that have more than one step. And this semester, we're going to be expanding on that concept, where we're going to learn many more reactions that have many steps. So it's important to recognize that most of those reactions are just a combination of those simple 4 different mechanistic patterns: the nucleophilic attack, loss of a leaving group, proton transfer, and a rearrangement. So for example, we can get from this secondary alcohol to this tertiary alkyl halide through a series of 3 steps. We have the first step is a proton transfer. You might recall that occurs because we're treating the alcohol with a strong acid, and strong acids will donate a proton to the oxygen, making a good leaving group, right? This is considered a good leaving group because once it leaves, it forms water, which is neutral and stable. It also formed a secondary carbocation, and whenever we form a secondary carbocation, we need to analyze for the possibility of rearrangements. If you can do a hydride shift or a methide shift from an adjacent carbon, and that makes the carbocation more stable, that can happen in solution. So in this case, they're showing a methide shift, get to this tertiary carbocation, and the last step is a nucleophilic attack, giving us this tertiary alkyl halide. Notice that some of these steps are drawn as reversible arrows and some of them are drawn as irreversible arrows. We're going to talk about when you can draw things reversibly versus irreversibly. Although the book is not necessarily consistent with always drawing them perfectly, but it is important to recognize when you can draw different types of arrows. Okay, and sometimes mechanistic steps can involve more than one pattern. So for example, hopefully you remember the term SN2, in an SN2 reaction, we have a nucleophilic attack and the loss of a leaving group occurring simultaneously. And so in this one step, we actually have 2 patterns. We have both the nucleophilic attack and the loss of a leaving group, right? And that can occur sometimes in different mechanisms. I'm just going to take a little break because I've been talking for a while, and I'll come right back to you. All right, let's get back to it. Okay, so I was just talking about how some reaction arrows can be drawn as a reversible arrow, and some are drawn irreversibly. So there are some rules to understand about when each of these can be used. Again, the book is not super consistent about always using the perfect arrow, but I think depends on the edition you're using. In edition 3 and 4, it's a lot more consistent than it was in edition 1 and 2. Okay, so let's talk about when we draw reversible versus irreversible arrows, or when we can. So when you're showing a nucleophilic attack, if the nucleophile is also a good leaving group, it will be reversible, right? Recall that nucleophilic attack and the loss of a leaving group pattern are essentially reverses, they're the reverse of each other. So when your nucleophile is also a good leaving group, right, we can draw in both directions, because the reverse process occurs at an appreciable rate. However, if the nucleophile is a poor leaving group, it's essentially an irreversible attack, right? So for example, a methyl anion is a type of nucleophile. It's a very strong nucleophile, and it will have a very easy time doing a nucleophilic attack, for example, on a carbonyl, and we'll see this reaction this semester. And because methyl groups are not good leaving groups, then this attack is essentially irreversible. So we would draw the irreversible arrow. How do we know it's a bad leaving group? So recall that good leaving groups are the conjugate base of strong acids, right? So if you're considering this as a leaving group, the conjugate acid is methane, which is CH4. And methane has a very high pKa of 50. So it's a very, very, very weak acid, which means this is a very, very strong base. And recall that good leaving groups are weak bases. So this would be a very bad leaving group. Essentially, carbanions are not very stable, so it's more difficult to form them because, again, the activation energy to go back is going to be very high. And so because we don't draw the reverse arrow because of a high activation energy, you can just draw this irreversible arrow. The loss of a leaving group is virtually always reversible, because if we're drawing the loss of a leaving group, we have a good leaving group, which means it's stable, and typically good leaving groups are also good or strong nucleophiles, so it will be reversible. Proton transfers are technically all reversible. However, if you have a pKa difference of 10 or more, it can essentially be considered irreversible, because remember, that means you have 10 to the 10 more products than reactants. So there's so few reactants that it's essentially an irreversible reaction because of very, very low concentration of reactants. So we would draw this one with a large pKa difference, much greater than 10, as irreversible. But when we have a small pKa difference, in this case only of about 2, this is definitely reversible. While there's 100 more products than reactants, there is some reactants in solution, so it is considered reversible, and we draw a reversible arrow. Carbocation rearrangements can essentially be treated as irreversible because there's no reason why a more stable carbocation would go back to a less stable carbocation. Call that there's no driving force. It doesn't happen, so we treat them as irreversible. When you're considering reversibility, you also need to consider Le Chatelier's principle, right? Because, for example, if you have a step where you're kicking off nitrogen gas and forming a carbanion, if this reaction was open to the atmosphere and the nitrogen gas was allowed to escape, then it would be impossible for the step to reverse. So you have to keep that in mind, that if you have escaping gases, right, that essentially can create an irreversible step. All right, let's move on to chapter 7, where we talk about different substitution and elimination reactions. So what we have right here is an SN2 reaction, where we have a nucleophile attacking in this case, a secondary alkyl halide to do an inversion. So recall that the nucleophile will attack from the back, right, donating into the carbon-bromine antibonding orbital. And essentially an inversion will take place where we invert this carbon, and we can see it's kind of like the umbrella flipping sides, right? And because the bromine and the sulfur both have the highest priority and often do, then the RNS designation also switch for that carbon. So it's important to recognize when you have a chiral center and you're doing an SN2 reaction, inversion is occurring. With SN2 reactions, the most reactive electrophiles are unhindered electrophiles. So methyl halides and primary alkyl halides react very quickly in SN2 reactions. Secondary alkyl halides are okay, and it depends on the nucleophile whether or not it will an SN2 reaction will occur. And typically, SN2 reactions do not occur on tertiary alkyl halides because they're too sterically hindered for backside attack. So let's talk a little bit about nucleophiles, because it is important to recognize that for an SN2 reaction, it requires a strong nucleophile. It requires a strong nucleophile because the nucleophile is concentration is important for it's involved in the rate determining step. So it's much more likely to be an SN2 reaction if you have a strong nucleophile versus a weak nucleophile. And how do we know, or what's the difference between strong and nucleophiles? Well, strong nucleophiles tend to have a greater concentration of negative charge. So for example, a full negative charge versus a partial negative charge. And in addition, they tend to be polarizable atoms. So it needs to have a decent size, like hydrogen with a lone pair and an anion is not a good nucleophile because hydrogen is a very small atom. And the larger the atom, the better. Right? So for example, if you compare hydroxide versus the sulfide, right, where HS minus, the sulfur atom with a negative charge and a lone pair will be much more nucleophilic than oxygen due to its greater polarizability due to the larger size. So polarizable atoms and ones that have a significant negative charge, like a full negative charge, tend to be great nucleophiles. Okay, let's talk a little bit about the E2 reaction. E2 elimination reaction is a reaction that utilizes a strong base to do an elimination to form an alkene. The reaction is regioselective, and if there's multiple different types of beta carbons, you can get multiple products. The products are related as constitutional isomers. And the Zaitsev product is the more stable alkene. And we know it's more stable because it's more substituted. So you can think of this as 1, 2, 3 substituents on these two carbons. So it's tri-substituted versus only 1, 2 di-substituted alkene. So whatever one is the more substituted alkene is more stable. We call that the Zaitsev product. The less substituted, less stable product is called the Hofmann product. And the regioselectivity of this reaction can be controlled by the choice of base. If you use an unhindered base like sodium hydroxide, methoxide, or ethoxide, the Zaitsev product will be the major product. If you use a bulky base like potassium terbutoxide, all of a sudden this reaction will favor the Hofmann product. And that's because there's some steric hindrance involved with bulky bases, and they will prefer the less sterically hindered hydrogens, as a result, giving the less substituted alkene. Let's talk about this E2 reaction. And it is, they call it a dehydrohalogenation because we're losing hydrogen and halogen during this elimination process. And this reaction, you actually need to figure out if you're going to get a Z or an E alkene. And it's not entirely clear which one you're going to get unless you do some work to figure it out, because this reaction is a stereospecific, And the reason I know it's going to be E2 and not SN2, for example, is because even though we have sodium ethoxide, which is considered a strong nucleophile and a strong base, we are dealing with a secondary alkyl halide. Secondary alkyl halides with strong nucleophiles / strong bases will prefer E2 over SN2. So it's going to, instead of doing SN2 and kicking out the bromine, it will take a proton from one of the beta carbons. If you look at this alpha carbon, which carbons are attached to it? There's two, right? There's this carbon and then this carbon. The carbon of the tert-butyl group doesn't have any hydrogens attached, so there can be no elimination across this bond. However, this beta carbon does have a hydrogen attached, so we can do an E2 reaction where we remove this proton, form a pi bond, and lose bromine all in one step. But we need to figure out which stereoisomer, which E or Z alkene will be the product in this case. And the reason why I know I need to do some work to figure it out is because I have an stereocenter at the alpha carbon and a stereocenter at the beta carbon. And when you see that you have both a stereocenter of alpha and beta, then the stereospecificity of the reaction will only lead to one product. And so we have to determine what that product is. And it is not always going to be the E alkene. Sometimes it will, but sometimes the exclusive product is the less stable Z alkene. So we need to figure it out. And the way I like to do that is with a Newman projection. So let's go ahead and draw that out. Okay, so what we're going to do is practice our Newman projection skills. We're going to place our eyeball up here, right, and then look down this carbon-carbon bond, where that's carbon 1, and that's going to be carbon 2. So again, I'm going to draw a circle with a back carbon with a dot for the front carbon. And then I'm going to look and see what my eyeball is looking at. I see this isopropyl group pointed straight down. So I'm going to draw that. And you can sort of draw it out, or you can just write I-PR for isopropyl. And then from my perspective, and I've got a group coming off to my left and coming off to my right, but the one that's going back is off to my left. So I have a methyl to the left, right, and a hydrogen over here to the right. And then carbon 2, which is in the back, has a bromine pointed straight up. Right? And there is a group coming again to the left and the right. And the tert-butyl is going to my left, right? So over here, and the hydrogen coming out to the right. Okay, what I like to do is actually just circle the groups that I'm really concerned with. Right? I know I'm going to be losing this bromine in an E2 reaction because that's the leading group, right? And that's attached to the alpha carbon, which is the big circle. The beta carbon is this front carbon, right? And it has the hydrogen that is going to be removed, right? So this is the beta carbon, this is the alpha carbon. This hydrogen is attached to the alpha carbon and it's not involved in the E2 reaction, so we don't care about it. But the goal is to get these two to be anti-periplanar or anti-coplanar. They need to be opposite one another, anti. We need to do a rotation. Right? So I'm going to rotate to get those two groups to be opposite. And you could rotate the front carbon, you could rotate the back carbon, you can rotate clockwise or counterclockwise, it doesn't matter. I am going to choose to rotate the front carbon clockwise 120 degrees. Okay, so I'm going to rotate front carbon clockwise fashion, right, 120 degrees, just so you can follow what I'm doing. Okay, so again, I'm going to draw my circle and my dot. Okay, I can go ahead and draw in the back carbon groups exactly as they were because I'm not rotating the back carbon. Okay, so I can just go ahead and draw those in. And then I'm going to have my front carbon rotated. Okay, so I'm essentially moving this here,
methyl group where the hydrogen was. So the hydrogen will move here, the isopropyl group is here, and the methyl. So again, focusing on the two groups that are important to me, the leaving group and the hydrogen that's removed.
I now have these anti to one another, which is great because this is the required transition state for the reaction to occur. Right? So now what happens is the base, right, which is our ethoxide, is going to come in and take this proton. We're going to form a pi bond, and we're going to lose our leaving group. And it all needs to line up because the sq3 hybridized orbital is going to turn into a p orbital, and the p orbital on this carbon must overlap with the p orbital on the back carbon to form a pi bond. So what that will look like after the reaction has occurred, so we'll say E2, right, occurs. We are going to have two carbons, and we can still draw them as a circle and a dot, but they're going to have flattened out because they'll be sp2 now as part of an alkene.
I'm going to just draw my isopropyl and my bromine completely opposite or 180 degrees
from one another. And then the p orbitals involved, right? So there'll be a p orbital on the front carbon and overlapping with the p orbital on the back carbon. So that's my pi bond. This is the pi overlapping p orbitals that make pi bond. On the back, I also have a tert-butyl, which ends up on the same side. It'll be a little hard to draw that. So I could watch to the side here. And a hydrogen. So this now shows how I should draw my product. So I have the double bond, and I like to sometimes just draw the double bond sort of in the same place where the single bond was, because that's where it's going to form between carbon 1 and 2. I have lost the hydrogen, I have lost the bromine, so those are gone. Right, but I still have a methyl and an isopropyl. And the first ones I draw in, I can draw in on any side I feel like. So methyl and isopropyl. Now I have to be careful to put the same group on the same side. Right? So on the same side as the isopropyl is the tert-butyl. So on the same side on a different carbon, I'm going to put the tert-butyl. And that there's a hydrogen here on the same side as the methyl. Right? So when I figure out is this E or Z, right, what we're going to figure out is that the tert-butyl gets priority over the hydrogen. Okay, so this is my priority group. And isopropyl gets priority over methyl. So the isopropyl and tert-butyl are my priority groups. They're on the same side of the double bond. So this is a Z alkene. And this is the only product. Right? E is not formed. Even though E is more stable, it cannot be formed because of the requirement for the anti-coplanar transition state. So that is a stereospecific E2 reaction where you have a chiral center at both the alpha and beta carbon, only one hydrogen at the beta carbon, and that's when you know you need to draw Newman projections to determine the correct product. When you're looking at stereospecific E2 reactions involving a cyclohexane, then we need to think about the fact that the reaction is going through a transition state where the structure is in a chair conformation because of the cyclohexane substrate. So one of the things we want to look at is we still have that requirement for the anti-periplanar transition state. But, and so when we draw the chair, the only way to get an anti-periplanar transition state is to have the leaving group in an axial position. That's really the chair that's going to matter when where this is in an axial position. And the equilibrium, though, between the two chair conformations will tell us whether or not the reaction is slow or fast, depending on which chair is favored. And then the stereochemistry of the hydrogen that gets removed will tell us whether or not more than one product can be formed. So I think it will make sense if I draw all this out so we can talk about these results. Okay, so we are going to start with drawing out the shear conformation of the two substrates. This one. And so I'm going to just draw, we talked about drawing chairs. Okay, so just follow the steps that we talked about before for drawing the chair conformation. And then we're going to draw both chair conformations. So it doesn't matter if you get the chlorine axial on the first try or the second try. So I'm just going to draw the tert-butyl here up and axial. I feel like it. And then the chlorine down and axial as well. So that's one chair conformation, but of course we know this chair can flip right to the other chair conformation. We're drawing that one out and sketch the other chair in as best you can. When we flip this, remember that this carbon flips down, so it's going to be up equatorial. And then this carbon is going to be this one now, and since we were down in axial, we'll be down in equatorial. So we'll put this one in the equatorial position of that carbon. So when you're thinking about which one is more stable, right, it definitely makes sense that the two groups being equatorial are much more stable than the two groups axial. So when I draw my little equilibrium arrow, it's going to be much more to the second chair conformation, which is much more stable. Okay, let's do the same analysis before we talk about this one anymore. Let's do the same analysis for the structure. We can do draw out the two chair conformations, just like we did in the first case. Right, so it'll be up tert-butyl group, and now we have an up chlorine, and then the other chair conformation. So the tert-butyl is the same, up equatorial now, and then the chlorine will be up and axial here. Okay, and when we think about which one is more stable, this big bulky tert-butyl group is definitely going to prefer an equatorial position. Even though the chlorine is axial, chlorine is much smaller than a tert-butyl group. So it's okay to sacrifice a chlorine axial to get tert-butyl in an equatorial position. So the equilibrium still definitely favors the chair conformation on the right. Okay, so let's think about this then. We're going to be able to explain now why this E2 reaction is slow and this E2 reaction is fast. Remember I said we still need the anti-periplanar or anti-coplanar transition state. And the only way to get that is when the chlorine is in an axial position. Because we're going to have hydrogens here and here that are anti to chlorine. Oops. Right? We were looking at, of course, the beta carbons. So that one was too far away. So we have these two hydrogens now that are exactly opposite the chlorine. So they're anti the chlorine in a Newman projection. You would see them as opposites, just like we did on the previous. Whereas over here, those same two hydrogens are not going to be anti to the chlorine, because anti to the chlorine right now is this bond. You can see that's opposite the chlorine, and this bond, which are not hydrogens. That's not really helpful. So this is definitely the chair conformation where the E2 reaction can take place from, and it's the major chair conformation because it's more stable. Over here, we have a situation where the major chair conformation is the not the conformation where an E2 reaction can take place. The E2 reaction can only take place from the conformation on the left, which doesn't which forms very slowly. So the concentration of this in solution is very low because it's very unstable.
So it's going to be a very slow reaction because it requires a chair that is not very stable. This is tert-butyl group. So this hydrogen here actually is not opposite the chlorine, so we cannot remove it. The only one that's opposite the chlorine on a beta carbon is this. Right? You can think of this position as blocked. Opposite the chlorine is the tert-butyl, not a hydrogen. So this one, which is this one here, you cannot remove it because it never gets anti the chlorine. The only one we can remove is the one over here, right, which is the up hydrogen on this carbon. So it's this one, right, that ends up being the only one that can be removed along with the right? And then with this structure, we have two hydrogens that are opposite the chlorine on different beta carbons. So in this case, we do have this one which can be removed, and also the one that's going down over here can be removed. Not the one that's up. The one that's up is not opposite the chlorine. So that's why we can get only one product in this case, because we only have the possibility to remove this hydrogen because of the requirement that they're anti in the transition state. Whereas now we have the possibility of removing two hydrogens on different beta carbons, forming two products. Technically, this one will be the major product because we're using a small, non-bulky, strong base. And this is the Zaitsev product. We know it's the Zaitsev product, right? Zaitsev major, because it's the more substituted, more stable product. This is a tri-substituted alkene. This is a di-substituted alkene. So tri-substituted alkene is more stable. As a result, it's the Zaitsev product, and with a small non-bulky base, it will be the major product. And of course, with only one product form, we don't need to say that it's the major product. Okay, let's talk now about our unimolecular substitution and elimination reactions, the SN1 and E1 reaction. Oftentimes, these reactions compete because they share the same rate determining step, which is the loss of the leaving group step. So let's consider this solvolysis reaction and practice drawing a mechanism for it. So we have the reason why it's called a solvolysis reaction first is because the solvent is also the nucleophile. So when the solvent is involved in the reaction, in this case as a nucleophile, we can call it the solvolysis reaction. So it sort of plays two roles, both the solvent and the nucleophile. Ethanol is a weak nucleophile. It is not a strong nucleophile. So because it's a weak nucleophile, it's not going to favor an SN2 reaction or an E2 reaction. It is a weak nucleophile / weak base, so it favors, by default, it favors SN1 and E1 because it would, being weak, it would disfavor SN2 and E2. And a tertiary substrate is fantastic for a secondary, for an SN1 and E1 reaction because it's going to have a very fast loss of the leaving group step, which again is the rate determining step. Okay, let's go ahead and practice trying that out. So the first step, because we have a good leaving group, right, the bromine is a good leaving group, and we have a tertiary substrate, which is going to form a stable tertiary carbocation. The first step is just going to be loss of the leaving group. A lot of times I like to draw in, again, with lone pairs when I'm drawing a mechanism, just so it's really clear where all the electrons end up. So we have, again, loss of the leaving group. Make sure to draw that arrow properly. That will generate a tertiary carbocation and some bromine. Okay, from the tertiary carbocation, there's multiple pathways that can occur. We can do a nucleophilic attack to eventually get the substitution product, and we can also remove a proton at the beta position to get the elimination product. And we want to draw both products. So what we can do is I'm just going to draw this out twice, because there's going to be two different pathways leading to two different products. So in one case, we're going to get the elimination product. That's only one step away, so I'll go ahead and draw that one first. So if I draw in any of the 9 hydrogens at the 3 methyl groups, all of those can be removed because they're all equivalent, right, because of symmetry. So if we have a base that can come in and take this proton, we'll be able to form the pi bond here. Remember, our base is just the weak base ethanol. And I'm going to draw in some ethanol, right? And we're going to use it as our base to take a proton at the beta carbon, and then the electrons can shift over to form a pi bond. When I want to form the pi bond, I'm going to draw an arrowhead right in between these 2 carbons. So that will lead to the elimination product and byproduct, which is protonated ethanol. Okay, alternately, instead of acting as a base, ethanol can act as a weak nucleophile. It functions as both a weak nucleophile and a weak base. I'm going to draw it in again and now use it as a nucleophile instead of a base. So I'm going to have it do a nucleophilic attack directly at the carbon that's electron deficient. And so now we have the formation, sharing those electrons pairs to form a signal bond. And now we're really close to the product. All we need to do is remove this proton. We're going to call that a deprotonation to get to a neutral product. I also formed protonated ethanol again in that step. Oh, sorry, I did not. I did not form that yet because it just formed the bond, so we didn't protonate it. Okay, so I'm just going to draw in a second ethanol, and I'm going to use it to again deprotonate the substrate, and that will generate the product. And now I've got the protein. So I can label these steps if I want. I can label them, right, loss of the leaving group. Note that they are the common steps that we talked about. This is, again, this is a proton transfer, right? Because this is acting as a base to take that proton. This is considered a proton transfer. And also the ethanol can act as a weak nucleophile to doing a nucleophilic attack. And because it's not neutral yet, it's not stable yet, so we'll do a proton transfer to get to a neutral stable product. And that explains the 2 products. Okay, so let's try another example. What happens if instead of a tertiary substrate, we use a primary alkyl halide substrate? It's reacted under solvolysis conditions, but instead of using ethanol as a solvent, we're going to use water as the solvent. And in this case, it's going to be heated so we can get a good amount of product. And there's only one product that's formed, which involves a rearrangement. So let's talk about what will happen in this case. Okay, so again, we want to draw in those lone pairs. And here's the thing. You might want to start this off the same way we did before, where we just do loss of a leaving group. Right? So, but the problem is that if I do loss of a leaving group from this primary alkyl halide, I'm going to get a primary carbocation. Recall that primary carbocations are not stable like tertiary carbocations, and they're so unstable that they don't form. So we cannot just draw loss of a leaving group to generate a primary carbocation. Instead, what we can do is a simultaneous hydride shift, or in this case, I'm sorry, methide shift, along with loss of a leaving group. So if I essentially shift the methyl at the same time as the bromide leaves, I've combined steps, right? So I'm doing two things in one step, but it's possible because I generate a stable carbocation. Let's look at what would form here. So if I shift my methyl over, okay, the methyl will now be attached to that carbon, and I'm going to have a carbocation here, and I've picked off some bromide. This in one step allows us to go directly through tertiary carbocation. Remember, do not draw primary carbocations. They are too unstable to form. This is really loss of a leaving group and, right, simultaneous, you can call it a rearrangement, okay, or be more specific, a methide shift. And now the water will get involved. And some water. It's a solvent that's also acting as a nucleophile. By the way, this says the only SN1 product. It doesn't mean it's the only product of this reaction. Recall that when we use a weak nucleophile / weak base, nucleophile, water is a weak nucleophile / weak base, we typically get both SN1 products and E1 products. So there are E1 products, 2 E1 products that are formed as well, but this is the only SN1 product. Okay, so I don't want you to be confused. This is not the only product, it's just the only SN1 product. We also get elimination products from an E1 pathway where water, again, acts as a base and takes a proton at one of the beta carbons. But if it's going to act as a nucleophile, it will do a nucleophilic attack. And that will give us initially this charged substrate. Label this. And then I can use another water molecule to deprotonate it, similarly to the way I used the second ethanol in the previous example to do the deprotonation. And we will get to now product and some byproduct. So the point was just to talk about the fact that this product is not observed, right? Because we don't ever get a primary carbocation for the nucleophile to potentially attack. Instead, it goes directly to the tertiary carbocation, and the nucleophile ends up at the tertiary carbon exclusively. Okay, let's talk about sulfonates, specifically the tosylate, because it's going to be important in the second semester as well. So recall, if you have an alcohol substrate, the OH group is considered a bad leaving group for substitution and elimination reactions. So in order to make it a good substrate, we have a few choices. We can add an acid. Acids will protonate it to make a good leaving group. But alternatively, we can also form what's called a tosylate to make it a good leaving group. There are some advantages to using a tosylate as opposed to an acid. The advantage of using a tosylate instead of an acid is you can then do an E2 reaction if you want, because E2 reactions use strong bases, and strong bases are not compatible with acid. So we wouldn't be able to use an acid plus a strong base to do a reaction because those would just react together. Instead of using an acid to make a good leaving group, we can use a formatosylate, which is a good leaving group. And then we could, for example, do an elimination reaction with a strong base if we wanted to, or even a substitution reaction. If we used an acid to make this a good nucleophile, the water could leave to form a secondary carbocation, and then you could get a racemic mixture of substitution products, basically going through an SN1 pathway. If you want to make sure to do to get inversion, you would need to do an SN2 pathway and not an SN1 pathway. So in order to get a good leaving group, but make sure to do inversion, we have to go SN2, and the best way to do that is to form a tosylate and then treat with a strong nucleophile, which will exclusively undergo SN2 and give you an inverted product. So when we're converting that OH group to an O to a tosylate, we can just use the abbreviation TS, which is put on by the conditions TSCl and pyridine. The TS actually is this entire group, right? So it's a big group that's being abbreviated, where the sulfur has 2 double bonds to oxygen and this toluene group. So it stands for para-toluene sulfonic acid. And so that's what a tosylate is, but the important thing that you want to just keep in mind, more than the structure, is just that now we have a good leaving group that we can then feed this substrate to do SN2 or E2 reaction. Okay, so from chapter 8, instead of really going over all of the reactions again from last semester, what I decided to do is just put this slide up here, just because I think the most important takeaway that you need from this chapter for this upcoming semester in OChem 2 is for you to know the reactions. So you, if you've forgotten them, and 98% of you or higher will probably have forgotten these reactions, and that's okay. You just need to remember them again. So I really recommend that you make flashcards for all of these reactions. And you can use different substrates. So look in your book and look for other substrates that use these conditions to make a product, right? So that you're not only learning just this one example of the reaction, but you're looking at, okay, what does it look like on a different substrate as well? Again, you can find so many examples if you just flip through the pages of your book, look at the reactions it talks about, and make flashcards. And the way I want you to make your flashcards to study these is, the best way to do it is to make multiple flashcards. What you can do for every given reaction, for example, on the front side of a flashcard, you could put the reactants and the reagents and leave off the product, and then draw the product on the back side of the flashcard, right? So that you can learn how to predict the product given the reactant and reagents. Alternatively, you can also draw the reactants and the product on the front side of a flashcard and leave the arrow blank. And then on the back side of the flashcard, add in the reagents that you are testing yourself. If you're given the reactant and the product, do you know which reagents were used to produce that product? Less common would be to draw the substrate on the back and leave that off on the front side, just because sometimes that's useful, but for the most part, the substrate is pretty obvious. Okay, so definitely, draw. I would go through the book, if you have it, chapter 8 and chapter 9, and just any example reactions given these substrates you can find, make flashcards, and make 2 flashcards per reaction, because you want to test your remembering the reagents and predicting the products. And hopefully that makes sense, because you will need all of these reactions this upcoming semester. They're going to be important when we do multi-step synthesis problems. So you need to know these reagents and what they do. Okay, so please do that. And every night before you go to bed sort of thing, go through them. And you can place the ones that you got wrong or didn't know into a separate pile, and the ones you did know, and then go over the ones you got wrong again. Right? And if you're doing that every night, then you will eventually learn them all. So this chapter was all on reactions of alkenes, or addition reactions of alkenes to form different products. Here is the summary slide from chapter 9. This is reactions of alkynes to produce different products. And mostly we're looking at terminal alkynes as the reactant. And then you want to learn these reactions as well. Some of these are probably more important than others, but you won't really know that until you start using them. So just go ahead and make flashcards for all of them. Okay, I want to talk a little bit about radical reactions. So this was only one chapter in the book because there's not a whole lot of radical reactions to know, but it is still important. Recall that if we have a weak bond, that we can either shine light or heat the substrate up, and the bonds can break homolytically as well as heterolytically. So they can break heterolytically, and that's all the reactions we've been talking about, or remove 2 electrons at once. But they can also break homolytically, which means 1 electron goes to each atom that's participating in the bond. When that happens, we form radicals. And when we show the arrows for that, instead of using a double-sided arrow, we're going to use a single-sided, what's also known as a fishhook arrow, to show the movement of just 1 electron. The most important thing from this chapter to take into the next semester are the reactions. And typically what you want to know is, starting from an alkane, so basically synthetically, if you're trying to draw a multi-step synthesis, and it's starting from some sort of alkene where there's no functional group present at all, you only have one choice in the reaction that you choose. You have to do a radical halogenation reaction from chapter 10, because there are no other reactions of alkenes other than combustion, which is not helpful for organic chemists. It's only helpful if you're trying to drive a car, for example. But in order to functionalize this, you only have one choice, and that is to use a radical halogenation. So when you're tackling multi-step synthesis problems and you see the reactant is an alkane, just draw this set of reagents in. It's the only thing you can do. And we just want to remember that bromine is more selective than chlorine. So usually people use bromine and not chlorine. And the bromine will go on the most substituted position. So if there's a tertiary carbon, place it there. If you don't have that choice, place it on a secondary carbon, etc. Right? It will always go on the most substituted position. So that's something to remember as well. So the 3 reactions that we learned from this chapter are the bromination of alkanes, and bromine and light will allow us to form bromine radicals, which will allow us to halogenate or brominate the most substituted position. This is a very important reaction. In addition, you can do the anti-Markovnikov addition of HBr to alkenes. So when you're studying your reactions from chapter 8, which talks about the Markovnikov addition of HBr to alkenes, where the bromine ends up at the tertiary carbon, you can also add this reaction in to your chapter 8 reactions, where if you have peroxides in with your HBr in the reaction, then you'll actually end up with the bromine on the less substituted carbon, not the most substituted carbon. We call that anti-Markovnikov. And then if you use the same substrate, right, something with a double bond, and you use NBS instead of bromine or HBr, then you will end up doing allylic bromination. So we'll put a bromine at the allylic position. Recall that the allylic position is the atom 1 single bond away from the double bond. So if you place the bromine here or here, those would be equivalent positions. Those are 3 reactions you want to add to your series of flashcards that you're going to be making to review for this upcoming semester. Okay, let's do some practice problems. Okay, we're going to do a couple of multi-step synthesis problems, which may be something you only really touched on at the end of last semester when you were taking OChem 1 or maybe a few semesters ago, depending on how long it's been for you. And it's something that we're really going to expand on this semester. So we want to review how to tackle and approach these multi-step synthesis problems. And that's where knowing all those reactions that we talked about using flashcards to make is going to be extremely important. Those are your individual building blocks that you can put together to do these multi-step synthesis problems. But if you don't know any reactions, you're not going to be able to do these problems. So you've got to learn your reactions first. All right, let's do some problems. So how do we approach synthesis problems? Well, there's a couple of things that I want you to do. One of the first things I want you to do is to count the carbons, because you want to know if you need to add more carbons, in essence, do a carbon-carbon bond forming reaction. Or possibly if you're losing carbons, you want to know that you need to do a carbon-carbon bond cleaving reaction. So that's something to note. So we have 1, 2, 3, 4, 5, right? 5 carbons, and this is 1, 2, 3, 4, 5, 6, 7. So we are going to be adding 2 carbons, which means I need to do a reaction that will make a new carbon-carbon bond. And in addition, think about functional group changes. So overall, you're going to convert a triple bond to a double bond, and that's something you want to be aware of as well. Well, you might have remembered from the end of OChem 1, there is a way to make a new carbon-carbon bond when you have a terminal alkyne. When you have a terminal alkyne, you can treat that terminal alkyne with a strong base, and commonly used in the Klein book is sodium amide, NaNH2. Again, that will deprotonate the hydrogen at the terminal, leaving a lone pair and an anion. And then we can add in any unhindered alkyl halide to form a new carbon-carbon bond. Because I know I want to add 2 carbons, I'm going to use a 2-carbon alkyl halide. So 1, 2, add in a leaving group like bromine. Okay, so this will allow me to add 2 carbons to the end of this 5-carbon chain, but I have not yet done anything with the triple bond. So it's still there. Add those 2 carbons. Now I'm at 7 carbons, so that's good. But I still need to convert the triple bond to a double bond. And it looks like it just needs to be reduced to a double bond. And if it looks like it's a trans, so an E alkene. So in order to get a trans alkene, I need the dissolving metal reduction condition. So sodium metal in liquid ammonia will be a way to reduce an alkyne to a trans alkene. Okay. We have one more practice problem to do, and then there's lots of practice in the review activity for you to work on after you start working on your reactions. Okay, so we are going to be working on the concept of electrosynthetic analysis, and we want to eventually come up with a multi-step pathway to get from this alcohol to this alkyne. But what we want to do is review the idea of working backward. That's what retrosynthetic analysis means. It means sort of, how can I work backwards from the products to get to the reactant? And then I can a pathway from the reactant to the product, adding in all the reagents at the end. So again, first things first, right? Remember, we're counting the carbons. We have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. So we don't need to form any carbon-carbon bonds. We just need to do a functional group transformation. Specifically, we need to remove this alcohol group and end up with a triple bond. Carbons. So that's our goal. There's no way to do that in one step. We need to sequence a series of steps together that will eventually allow us to get there. So one thing we can sort of do when we're working backwards is we can use a retrosynthetic arrow. So for the retrosynthetic arrow, often we kind of use that arrow. So sort of, okay, what can I use to make that, right? How do I make triple bonds, right? So one way is to think about doing a double elimination. So to do to make a triple bond, we can do a double elimination from either it's called a geminal or a vicinal dihalide. So I'm going to put even some choices here. Okay, so I have chlorines. They could be attached to the same carbon. We call those geminal. Or they could be attached to adjacent carbons. We call those vicinal. So one of these two will allow me to do a double elimination to get to an alkyne. So I'm thinking about this one because this is helpful. I can make this one from an alkene. Right? So I'm sort of continuing to work backwards. Okay? I know that I can make that vicinal dihalide from a double bond, and I can just add chlorine, Cl2, to get there, just like you would add Br2 and add bromine on vicinal carbons, right? So that's allowed me to get back here, right? And then from there, how can I get to, is there a way to go from this directly, right, to that? Sort of, but perhaps we would like to have a good leading group if we're going to do an elimination reaction to get an alkene. Kind of continuing in reverse, right? And you can kind of, making it kind of messy, but you can keep going. Perhaps this team, they're working my way back to the reagents, right? Maybe I did an elimination of a tosylate, right, to get to the substrate. And then this would be getting me back to the starting material. I know that I can tosylate an alcohol. So I've got a series of a bunch of steps here that I need to do sort of in the forward direction to get to the product. Right? But this is at least sort of getting my pathway in place. So the first thing I talked about doing is making a tosylate. Right? So we need to remember that we can use TSL, purity. Sometimes people just write PY or PYR for purity. And that will get me to tosylate. From there, I can do an elimination to get the alkene that I talked about. So you can sort of work your way to the pathway that you had envisioned. Okay, and what sort of conditions do I want to use for this elimination? So it's going to be an E2 reaction. And I don't have to worry about Zaitsev versus Hoffman because this is the alpha carbon, there's only one beta carbon, so there's no issue of removing a beta carbon from different beta carbons. But E2 means strong base, right? Only one beta carbon means I don't have to worry about bulky versus strong base. But I think I'm going to use bulky just because this is a primary substrate, and if I use a small one, it might also act as a and give me some SN2, which I don't want. So I'm going to use a bulky. Not because I'm worried about Hoffman versus Zaitsev regioselectivity, but more because I want to prevent SN2, which is primary substrates are great substrates for SN2 reactions. And if I was to use hydroxide, then it could just do SN2 major and only E2 minor. So using a bulky nucleophile will prevent SN2 and favor E2. Okay, from my alkene, I talked about then adding some chlorines. And again, I put chlorines, but they could be bromines as well. Why don't we go ahead and use bromine? So I'm going to just change that to bromine. Then my substrate will just be Br2. And then I just need to do the double elimination to get to the alkyne. Go directly from here to the product. And the book talks about using excess NaNH2 multiple equivalents. We need 2 equivalents to do the 2 eliminations, and a third equivalent to deprotonate the terminal alkyne. And then we need a water workup to reprotonate the alkyne and isolate the alkyne product. So the actual answer is just this part. The rest of it was utilizing a process called retrosynthetic analysis to help us figure out a pathway to use. Okay, I believe that is the last slide. So I will just say, welcome to the class. I know this is, your first week, and you are hopefully being devoted to watching this video, making your flashcards, reviewing. It's going to be really important. You only have a week to review, and then we're going to get into new material. So I will see you guys in office hours, and let me know anytime if you need extra help.